Okay, well, thank you, David. My talk today is going to be about Kagome spin liquids and nuclear relaxation in Herbertsmithites. But for the most part, it's really going to be a fairly general introduction to the subject of Kagome spin liquids. So some of the recent work was done in collaboration with a student, Nick Sherman at UC Davis, and a very prominent NMR experimentalist, Takashi Imai, who's at McMaster in Canada. And previously, actually, I've worked on this Kagome problem in collaboration with Jan Oikma at New South Wales in Australia, Marcos Rigol, who was a postdoc at Davis and now is a professor at Penn State, and David Hughes, who's at Princeton. So the outline for my talk is as follows. So basically, I'd like to begin with a general introduction to the subject of quantum spin liquids, and then discuss the current status of this Kagome Lattice Heisenberg model. The Kagome lattice is depicted here. It's a name gotten from this Japanese basketry, but has become really an important topic in the study of quantum spin liquids, really. So I'll discuss what is the current state, why this is such an important model, and what is the current status. I'd also then discuss these particular materials that have Kagome structure, and to what extent do we think there is a quantum spin liquid phase realized in these materials. And then briefly talk about our recent work on NMR relaxation rates and discuss what light it throws on these systems, and then end with some summary and conclusions. So we can basically think about the phases of an ensemble of spins in analogy with the phases of a atomic system as atoms move around and form solids, liquids, and gases, basically, something that we are all very familiar with. So in some sense, just like in case of atomic motion and arrangement, the spins at low temperature basically solidify, if you like, in crystalline arrangements. They either form ferromagnets if they have a ferromagnetic exchange interaction, or they like to form an antiferromagnet, or some other more complex crystalline structure, really. So energy usually favors these structures. So at low temperature we have these phases, and at high temperature basically they fluctuate independently, where every spin is fluctuating independently like a spin gas in a paramagnet. So these are the two, of course, most common phases favored by temperature, by energy, and by entropy. The question arises, do we have a well-defined liquid phase? As we know, a liquid phase is not really a distinct phase from a gas. Basically one can go from one phase to the other in a continuous manner, but it's a really important phase, clearly, where the short range order is very well defined, and yet there's complete fluidity, things can move around. So in case of spin systems, usually there's a direct transition, one would say, between this phase and this phase with no intervening phase, but there are cases where there's a fairly well defined liquid phase, and an example of that is something known as the spin ice. So spin ice basically is a phase where we have a spin system of corner sharing tetrahedra, and each tetrahedra has 4 spins, all equidistant from each other, and one imagines that this system is strongly anisotropic. So each spin can point in or out basically towards the center of the tetrahedra, and if the interactions are such that 2 of them must point in and 2 of them must point out, this problem maps exactly onto the problem of the ice problem, which was discussed by Linus Pauling and various other people long time ago. So it's called a spin ice, and such a problem, if we consider just a purely classical system, is known to form all the way down to as low a temperature as you can go, basically a state where every tetrahedra is completely every tetrahedra obeys the ice rule, yet there is no long range order there. So in that sense you have fully developed short range order, but no long range order in the system. This is an example of a classical spin liquid system. The question really is that I want to discuss here is, what about a coherent quantum liquid? So can we have in presence of quantum fluctuations, can we have basically a quantum spin liquid form exist all the way down to 0 temperature? So from this atomic a motion point of view, this is like having a superfluid phase in the system. So, this subject of quantum spin liquids really goes back at least to the work of Phil Anderson in the early 1970s, when he proposed that the ground state of a triangular lattice Heisenberg-antiferromagnet should be a resonating valence bond state. And we know that if we just have two spins coupled antiferromagnetically, they like to form a spin rotationally invariant singlet state. And basically, if the spins are all tied up in pairs like this, such a state would be called a dimer or valence bond configuration. And the idea of a resonating valence bond state is that the ground state is some linear superposition of a very large number of such states. Okay, so this particular idea remained dormant for some years, but really after the discovery of high temperature superconductivity, it really became very prominent, because Anderson actually suggested that the mechanism of high temperature superconductivity was closely tied to the formation of such quantum spin liquids, and that doping of such quantum spin liquids will immediately result in a high temperature superconductivity. And lots of authors worked on that after that. The connection with high TC superconductivity is not so clear, and is in some sense this subject has sort of diverged from the study of superconductivity itself. But there were lots of experimental investigations in the meanwhile where people were looking for systems where there was a quantum spin liquid, and for a long time what should one experimentalist look for was not so clear. There was a vague idea that a quantum spin liquid is something which is not this, which is not that, which is not this, but what is it was not clear. In other words, it was a system that did not have long range order, so no long range spin order. It was a system that did not break translational symmetry, it did not have any valence bond type order, but what should one look for? So for example, could we just have a system with say where the magnetic system consists of pairs of say spin atoms which are then well separated from other pairs, and such a system will obviously form spin singlet, but should one even call such a system? They were being called by some experimental groups as quantum spin liquids, but I think in the last few years this idea of what a quantum spin liquid has crystallized a lot more. It's really an emergent state of matter that cannot be adiabatically connected to any kind of product state, a state which is a product over decoupled clusters. So basically such a emergent quantum spin liquid state essentially has these properties. These are really key properties really. First, there is a fractionalization. That is, in general, from a mathematical point of view, one can always express say a fermion operator, let us say with a spin, fermion destruction or creation operator, in terms of a pair of operators. Such a mathematical transformation is always allowed, where you say that this operator, let us say, carries the charge degrees of freedom, and this operator is a boson, and this operator carries a spin degree of freedom and is a fermion. One can always make such transformation, but when do these objects actually become deconfined and independent degrees of freedom? That is not obvious. So a quantum spin liquid is a phase where these objects really become independent degrees of freedom. However, the system remembers the fact that ultimately the microscopic degrees of freedom are electrons, and that means there must be some constraints that these guys obey at every site, which arises from the fact that they came from electrons, and that necessarily, whenever we make such a parton construction, it necessarily leads to an emergent gauge theory. Okay, so what kind of emergent gauge theory, that will depend on what kind of spin liquid we have, and such a phase always arises with non-trivial, non-local quantum entanglement. So yeah, so okay, basically quantum entanglement in most systems, the quantum entanglement is essentially local, is related with if you divide a system into two halves and ask how entangled are the microscopic degrees of freedom on the left with those on the right, that entanglement usually turns out to be local, associated with the degrees of freedom which are right at the boundary. But in these kinds of systems we have non-local quantum entanglement, and in particular in certain kinds of spin liquids one can actually define a topological entanglement entropy, which is really a universal characteristic of the spin liquid phase.
Quick question. When you say that it's not connected to any product state, the pictures above kind of do look like product states of singlets.
Right, each one of them. Right, but so it must be an infinite superposition really, such a massive superposition that it is not.
So by product states you really mean here like the crystalline states that you started with?
For example, or any one of them I would call a product state, but the massive superposition is no longer connected to any one product state. Okay, so if once we that discussion of what a quantum spin liquid was from a theoretical point of view. So what are the challenges then if one wants to actually look for such a quantum spin liquid in experiments? So the first real challenge is that the entanglement cannot be measured directly. I mean, in cold atoms people are starting to measure such entanglement with tens of spins, but really this is really a highly non-local many-body measurement. Is really not possible to scale it for a system with thermodynamic number of spins, really. So one has to look for some.
How do you expect entanglement to scale?
This actually, okay, so I didn't, I had a slide, I removed that slide about quantum entanglement really. So quantum entanglement usually satisfies area law, which is associated with the boundary, and then if you have lower dimensional manifold there will be some line law, etc., some corner law. So this is in addition to those, if you can somehow remove those, there remains a non-local entanglement which represents some kind of a constraint running through the system. So whenever you have such an emergent state, there is a number, there is an additional actually reduction in entanglement that comes from this. And so it's not easy, even in numerical studies measuring this quantum entanglement is not easy, because the other parts of the entanglement are actually much bigger in magnitude. So it's a sub-leading quantity really. Okay, so really what one has to focus on, and for many years the focus really was on these as emphasized for example by Patrick Lee, what one would like to look for is various kinds of power laws whose powers can be predicted, for example in temperature dependence or dependence on some other parameter, in thermodynamic as well as transport properties, in heat capacity, in susceptibility, thermal conductivity, etc. And in particular if one takes for example this picture of deconfined degrees of freedom, from there one can theoretically obtain these power laws and one can hope to compare that with experiments. So this approach however has the problem that basically it can easily be corrupted by something other than what we are looking for. I mean, how do we tell that these power laws are really coming from our quantum spin liquid and not from something else like phonons or impurities or anisotropies, etc. So this is not really a smoking gun kind of an experiment. The thing that is I think much more direct is really looking for these fractional degrees of freedom, but again the thing about fractional degrees of freedom is that they are necessarily confined, they are new particles that only live within that phase, they cannot come out of the phase, and they also cannot directly couple to external probes. So if we have a neutron or a photon coming out from outside of the system or an electron coming from outside and leaving the system, these objects must have normal degrees of freedom. So the fractional degrees of freedom, they live only inside our material, and that means that the continuum, what one should see really is that there should be a continuum in any scattering measurement rather than what one usually sees. So this is a cartoon taken from Leon Bellin's review over here. So in an ordinary magnetic system what happens is spins are ordered in some way. If we look for example for a usual spin flip is the normal kind of excitation which will turn into a magnon or a spin wave. Basically the scattering, if one looks for, on this axis, if I plot the momentum transfer and on this axis I plot the energy transfer, there is usually a well defined energy momentum dispersion where these excitations live, and not surprisingly the scattering intensity will be mostly right at these energies, and it will have a strong fall off away from these energies. So that is a normal signature that one sees in a magnetically ordered system. So in contrast, when we have a system with deconfined spin half objects, then the energy momentum, the scattering for any external probe should look something like this. So if this is the momentum axis and if this is the energy axis, then typically for a given momentum there will be a whole range of energies where one sees the scattering, and that reflects the fact that basically the magnon in this case is actually a composite of two free spin-ons, and each spin-on basically can have a certain energy, and this energy at a particular point over here is made up of sum of two energies, and as you vary the two energies basically you can get a whole range of different values at which scattering can happen. So really this is one of the key methods by which one can look for quantum spin liquids. Yeah.
Roger, question. Suppose someone can map out the boundary of the spectrum.
This one.
Right. But still trace out the spin half spin-on. Because this is like if you imagine the spin-spin correlation function, right? And they are made of the a superposition of spin-on. It's like more like a lot of Green's function products contributed to the spin-spin correlation function,
right,
which can be measured. But fundamentally, the quasi-particle in this new state is more like a spin-ons,
right,
spin, no charge.
Right.
So suppose someone can say you measure the spin correlation function. So it's like incoherent because it's like for given.
You're saying that the
what if you map, so is the boundary very sharp?
The boundary is supposed, in most of the models at least, the boundaries are very sharp, yes. So for example, the one case where things are really well studied and completely solved is the one dimensional quantum spin chain solvable by beta ansatz, and there one knows exactly what the boundaries.
About the energy spectra.
I know. If you look at the continuum, let's call it the two spin-on continuum. The magnon spectrum will contain 2 spin-on continuum plus 3 spin-on plus 4 spin-on, etc. But let's focus on the 2 spin-on, which has most of the spectral weight actually. So the magnon, the lower boundary in particular, in that case the lower and the upper boundary one can calculate analytically, and they are indeed very sharp. There is, the scattering exists between a lower boundary and an upper boundary, and the boundaries are actually, the lower one is actually has a name even, it's called the de Closaux-Pearson spectrum after the people who first discovered it, except it's not like a spin wave, it's just the lower boundary of a continuum. So in that sense you are right that just the lower boundary itself can be, but this is, I think, a model dependent statement.
You think about your spin correlation function is a product, the integral of 2 Green's functions.
That's right.
But it's, so how can you get a very sharp boundary?
Well, in one dimension you do. So
this is 2D.
This is 2D. So it's not obvious to me that this will, you can easily infer the.
You have a finite contribution.
Yeah. So it's
all possible energies. If I think, if you just like.
No, we will see. There can still be cutoffs. There could still be no solutions in certain regions. There could still be sharp cutoffs. But that does not.
You say if you have a quasi-particle which is very sharp, you definitely get the very sharp for the spin correlation function. Suppose you take Fermi liquid. Suppose you have quasi-particle
at zero temperature.
At zero temperature, do you always get the very sharp boundary for the spin excitations?
There might be some. There might be.
Suppose you take the Fermi liquid as a model. You just say take Fermi liquid. There's no spin order, but you just want to say I want to calculate the spin correlation function for a spin liquid with 2 spins.
Right.
Do you get a sharp boundary for the spin correlation?
No. Well, you certainly get a sharp upper boundary, right?
You have finite energy to find out.
I know. You get a sharp upper boundary, but I think you can get sharp lower boundary also. It depends on. It might depend on whether the minimum.
It's a convolution of
That is correct. That is correct. So you are adding up the energy of two objects, if you like.
Yeah.
And the question is, for a given momentum.
Because the difference can be from 0 to.
Yeah, but even okay. So I think for a Fermi liquid, you'll get something like this. Here, it'll be 0, but then it'll be like this. There will be, for a given momentum, you cannot get that momentum at 0 energy. You see what I'm saying? If even for a Fermi liquid, if you fix some finite momentum, then the pair cannot get lower than a certain energy. You see what I'm saying? The best you might be able to do is.
It's not on the physical shell. You're talking about the.
Yeah. But yeah. So no. I'm saying if you add up the energy of two fermions, okay, and I want to get a total momentum fixed. So I have a momentum, let's say k, and the momentum k is being obtained by adding a fermion of momentum q and a fermion with momentum k minus q. Okay. So given a k, there will be a minimum energy that below which there will be no such state of two fermions. So in a Fermi liquid, the energy will start from 0 at 0 momentum, but any finite momentum, again there will be a minimum. Okay, that's typically.
If that's the case, actually, this already shows evidence.
Yeah. If you don't see a sharp continuum like this, instead a sharp mode like this, instead you see a continuum, that would be a signature.
Yeah, the trace of the boundary can
yes.
give you some evidence. Great.
So actually I have another question. For something like an ordinary magnet, there could also be corruption from things like phonons, because you could excite a magnon plus one phonon or magnon plus two phonons.
That is correct.
So
but usually that causes some broadening.
So I would expect that above at that low temperature, this would determine the bottom of the absorption spectrum, but there would be a continuum above it.
That I think that is a correct statement.
So how do I tell that continuum from that continuum?
Well, okay. So I think in most materials, these lines are actually pretty sharp. But especially as you go towards lower and lower temperatures. Right. But you're right. I mean, in some sense, the problem of phonons and impurities can make these sharp features also look more like a continuum. So we'll see some examples of what's the best that people have. Okay. Now, the thing on which there has really been a lot of progress recently is the synthesis of candidate quantum spin liquid materials. So first of all, there are a number of triangular lattice antiferromagnet, and this particular one was published in Nature just a week or two ago by this Chinese group. It's a terbium based system which forms a triangular lattice antiferromagnet, where they argue that they have a quantum spin liquid that shows this continuum scattering. There's also been a lot of interest in what are called quantum spin ice problems. That is,
sorry, is it a 3D material?
This one?
Is it two-dimensional?
It's a two-dimensional, quasi two-dimensional material. Layered structure, right? Yeah. This is a three-dimensional material. So it's not like quantum spin liquids only arise in 2 dimension, they can also happen in 3 dimension. This is something known as a Kitaev spin liquid or a Kitaev-Jekeli-Khaliulin material. So these are materials which are strongly anisotropic, where the spin coupling along the 3 bonds of this honeycomb lattice are only along the x-axis. Only the spins along the x-axis couple Sx, Sx, Sy, Sy along this axis, Z along this axis, and it turns out that a model like that can be solved exactly as shown by Alexei Kitaev, and has it can be solved exactly in terms of Majorana fermions, has an exact ground state, and there are actually claims of materials that show that kind of spin liquid phenomena.
So I want to learn from you the language the community uses, because for this model, of course, solved exactly, and you demonstrate a spin like you fractionized.
Right.
But actually, you don't have full spin symmetry, right?
Right, that's true.
So do they still call call it a spin liquid?
It's still called a spin liquid, yes.
You're full. I mean, you know what I mean, right?
Yeah, you don't have to have, you do not necessarily have to have full spin rotational symmetry.
This has nothing left.
No, this has no such symmetry left.
Right.
So the important thing, however, is that your elementary degrees of freedom are spin objects, where you would naively think that flipping a spin will cause a spin 1 excitation, but the elementary excitation of the system has become fractionalized. Okay, so in that sense this is still a spin liquid. And of course the one that I am going to focus on here are these Kagome materials, which are related to these
how
minerals.
People interpret the keyword liquid in this definition?
Sorry?
What does liquid mean in the spin liquid? When the people talk about spin liquid, liquid means you don't have the symmetry, or
No, so the spin rotational, the liquid means that the system has not solidified into some kind of a crystalline arrangement, and there's still a fluidity. The spin system continues to fluctuate in a coherent manner.
There's still some symmetry left.
Well, symmetry.
The ground state still has the same symmetry as the Hamiltonian.
Yes, okay.
But
That certainly is true.
With a K-type model, you don't have the symmetry to begin with.
Yeah, so symmetry, no, so
the liquid is not really meaning
no, but you could still have some kind of a periodic arrangement of something. So you have not broken any of this.
But that's not spin part.
That's not the spin part, but the symmetry also includes that. When you say a liquid,
that's like charged liquid.
Yeah, when you use the word liquid, it means that it is neither neither breaking the spin symmetry. So one way to, of course, form a so here also it's possible that the spins, all prefer to order along the z-axis, even though you have no.
Here the symmetry is not there. There's no symmetry to start with.
There is a.
They just want to point out
there's no spin. There is no SU2 symmetry of the spins.
There's no symmetry. You have this spin can depend upon the orientation. There's no spin. This is not icing.
There's not icing.
There's no spin symmetry in this part.
The symmetry can be regarded as a combination of space group rotation and spin rotation.
Then
if you combine these two, that's a symmetry.
They have spatial symmetry.
They have spatial. So you could still imagine a system that will, at the end of the day, break some symmetry and form some kind of a lattice, super lattice.
So the community still think this.
Yeah, this would be called a spin liquid. The more important thing is that we are getting these fractional degrees of freedom. Right. Okay, so what is this Kagome-antiferromagnet? So the Kagome lattice is basically a lattice of corner sharing triangles, and triangles basically have this property that if we consider, for example, an Ising model, spin half Ising model, it can take two possible values at each lattice site, and that means the triangle can take 8 possible configurations, but 6 out of the 8 are actually ground state. They are the lowest energy. Only the configuration where all are up or all are down are not a ground state. So a huge degeneracy is a general feature of frustrated magnets, really. But when we have a lattice of corner sharing triangle, that is significantly more frustrated than a lattice of edge sharing triangle. So a triangular lattice, basically one would be where these center of the hexagons will also form lattice sites where we have a spin. So essentially a Kagome lattice is a 1/4 periodically diluted triangular lattice. So if you consider now, let's say both these models, the Ising model on Kagome and triangular lattice are both exactly soluble. It's known that the triangular lattice model has remains disordered down to 0 temperature, but the correlation length diverges. Essentially the 0 temperature is like a critical point, but for the Ising model, for the Kagome lattice, all the way down to 0 temperature the model stays disordered with a correlation length which is only of order the lattice constant. So really strongly disordered, and there's a huge ground state entropy in both cases, and Kagome lattice, it's a very large fraction of the state remain still accessible down to 0 temperature. But what's interesting is that if we go to Heisenberg model, now let's consider just the classical Heisenberg model. So spins can orient and point in any direction. Then if you consider any triangle, or let's take this triangle over here, the spins basically need to form a 120-degree structure. That is, the lowest energy configuration on a triangle is one where the spins point along 120-degree angles. If we have a triangular lattice, not a Kagome lattice, then it turns out that once you fix the spins on one triangle, every spin on the lattice gets uniquely fixed, because when you share bonds, then if I fix the spin on this triangle, then these two basically end up fixing this spin, and then these two end up fixing this spin, and the order propagates through the entire system, and the possibility of canting actually completely removes the frustration, and the system is no longer really frustrated in that sense. But if you consider a classical Heisenberg model on the Kagome lattice, because it's a lattice of corner sharing triangles, the order doesn't propagate from one triangle to the next triangle, and in fact one can show that one still retains an exponentially large number of possible configurations that remain exactly degenerate. In fact, it is, after a lot of numerical studies, the Kagome lattice is one of the very few cases where purely nearest neighbor Heisenberg model may have a quantum spin liquid ground state without adding any extra perturbation to the system, really. Okay, so there have been a lot of studies of the Kagome lattice. So first of all, even in such a highly frustrated case, a very common thing that happens is selection of order by disorder. If we have quantum fluctuations, entropies usually get removed, one third law is obeyed, and usually one gets to some kind of a selection of ground state, and usually the phenomena that dominates is order by disorder. Some particular configuration actually is picked out by quantum or thermal or other kinds of fluctuations, really. So a few different ways of studying this model, for example, is let's study the structure factor, say for the classical model in a high temperature expansion. What one would find is that it remains independent of Q up to order beta to the power 7, but then at a higher order basically there is a selection, there is some Q value at which the structure factor starts to grow, and essentially at the end the model ends up ordering. So similarly, if we go to 0 temperature, yes.
Sorry, what is Q?
Q is the momentum in the Brillouin zone. Sorry. So S of Q. So basically at every, this is a lattice with three spins per unit cell. So structure factor is a 3 by 3 matrix really for every Q value. And what one finds is that the largest eigenvalue is independent of Q up to some order, but then at some higher order selection happens and spins begin to prefer to order in a particular way. And the same thing happens actually if you study the system at 0 temperature basically. So you can show that if you start with any 120-degree ordered configuration and carry out either nonlinear spin wave theory or real space perturbation theory, it remains degenerate up to some high order, but then an order begins to get selected. But then if quantum fluctuation become too large, then they end up destroying this kind of order. And the phase diagram that we believe is correct really is that if this is an anisotropy axis, so delta equals 1 corresponds to the Heisenberg model, 0 corresponds to the Ising model, and S is the spin quantum number. So anything 3/2 and higher actually get ordered due to this order by disorder phenomena. The only thing that does not get ordered is spin 1 and spin 1/2, and in fact the spin 1 ends up dimerizing in some or trimerizing rather. It starts to form a different type of an ordered pattern where the down pointing spin have a different correlation from the up pointing spin. So really the spin 1/2 model is the only candidate for a quantum spin liquid, and much of the information about quantum spin liquid really comes from looking at the spectra of finite systems, and you can see the clear difference between say a square lattice, a triangular lattice and a Kagome lattice by just looking at the spectra of 36 site. So for example, this is the square lattice. One can see the sparsity of the spectrum over here. On this energy scale, they all have a J of 1. On this energy scale, there are very few states over here, and these states S equal this plot really on this axis we have different quantum numbers of the system. So this is S equals 0, S equals 1, S equals 2, and they are the momentum quantum numbers are labeled over here, which one does not need to read really, and on this axis is the energy. And what you find is that this state and this state are far below anything else. And in fact, there is a simple theory of spontaneous symmetry breaking that one can develop, which tells you that it is actually the linear superposition of these states that gives us the null state as a state with spontaneously broken symmetry. And so these states should separate out from everything else and really go to 0 as 1 over n, whereas any other state will only go to 0 as 1 over square root of n. And so that picture is very clear when we look at the spectrum of the square lattice. Actually, something very similar happens for triangular lattice, although it is not as well separated. The energy scale is reduced, but you can see the spin 0, the 2 spin 1 and the 3 spin 2 states are separated from the other states basically in each sector. And now because we have a 3 sublattice structure, it turns out again this theory of spontaneous symmetry breaking will tell you exactly what the count and what the momentum of those states are going to be, and it will be the linear superposition of these that will give us long range order. So we believe a pure triangular lattice Heisenberg model actually develops long range order. But if you look now at the spectrum of the Kagome lattice, it looks very different. On this scale, which is a much lower energy scale, you have first of all a huge number of spectrum, and furthermore what you see is within the singlet there are massively large number of states below the lowest triplet state. So below the lowest triplet there is a very large number of singlet states. So somehow the singlet states are dominating. The physics has no relationship to this spontaneous symmetry breaking, which leads to antiferromagnetic order.
Excuse me, I have a question about last slide. Yeah, this one. By all those models, are you only using the nearest neighbor?
Yes, this is only nearest neighbor.
Okay, this is DMRG result.
This is exact diagonalization.
Oh.
So this is a 36 site cluster with periodic boundary conditions for which one can do exact diagonalization.
Okay, I see.
Yeah. So people have looked at these problems with J1, J2, etc. You never get anything like as complex as this. They get more energy. The energy scale of the problem does go down, but you never see something like this where you have a huge number of singlet states below the lowest triplet state. I have not seen this happen in any other model.
Okay. But the thing is that you said also for the J1 and J2 model for triangular lattice, people doesn't see it.
No, not like this. Yeah, this is very unusual that you have such a large number of singlet states below the lowest triplet state at a very, very small energy scale.
Okay.
So that's unique to the Kagome lattice.
But I think there are some recent publications saying that the J1 and J2 model for triangular lattice might be a spin
Liquid of a different kind actually, yes.
Okay.
That is correct,
And
yeah.
Another question is, you said if there are low-lying states that goes to 0 faster than the others, it might be an indication that those low-lying states are symmetry breaking states.
Yeah, so in this case so if the system has Néel order, then the symmetry that will be spontaneously broken is very well understood, and you can show that symmetry breaking will be basically coming from symmetry breaking means that spin will no longer be a good quantum number, and that symmetry breaking amounts to considering a ground state which is a linear superposition of these different spin states, and one knows exactly what the structure of these states would be in a finite system then, whose linear combination, how many singlet state, how many triplet state, how many spin 2 states, etc. will there be, and what their momentum quantum number is. Everything can be worked out exactly. And so these two cases, it exactly fits with this spontaneous symmetry breaking picture. Okay, there is no such thing going on here. That's pretty clear.
Okay, thanks.
So actually, I was wondering what is the state of the art, or are you going to tell us?
I was just going to say that people have been able to do up to 48 spins, which is quite amazing. Exact diagonalization.
I see.
Yeah.
I seem to remember Brian Clark doing some trial projected wave function approach to this, which shows that it does crystallize. Do you know anything about that one? But maybe
Not sure. Yeah. I'm not sure. So I think I'm running a little bit late. maybe I could just say that the one thing that we tried was basically try again an expansion, because there are huge number of singlet states. You can start from different kinds of valence bond configuration and try to calculate the energy around any one of them, and what you find is that essentially you get very close energies and not too far from what was anticipated to be the ground state energy at the time of the numbers that we were getting. But more recent DMRG study clearly shows that this valence bond singlet states is not the correct ground state, but the correct ground state is a resonating quantum spin liquid state, which has an energy even lower than this. So let me just quickly flash this this thing on DMRG studies, which has been very important. Basically DMRG is a method meant for studying one-dimensional systems, but they have also succeeded in studying two-dimensional system, basically by considering it as a on a finite cylinder, by essentially considering the two-dimensional system as a one-dimensional system with some longer range interaction. And the things that they find basically is, first of all, that the ground state energy, the claim is that the ground state energy does not have much size. This C, let us say, is the transverse direction over here, which is limited. They cannot do much bigger than 10 on this direction over here, or much bigger than 12, which is like 6 unit cells. But the claim is that there is not much size dependence to the energy over here, and they can get a energy which is much lower than what we were getting from these different perturbation theory around different valence bond configuration, giving us evidence that there is an extra lowering of energy due to the resonance. There is also a calculation of entanglement entropy by this group over here of Leon Balance and collaborators, arguing that there is an entanglement, there is a topological entanglement entropy which corresponds to that of a Z2 spin liquid. And there is also the claim that somehow this very large number of singlet states and the difference between the singlet and the triplet gap is not really visible in the DMRG studies. It tends to show that with increasing size, basically the singlet and triplet gaps become comparable. But I am not completely convinced that DMRG is actually getting the whole story right. So the question, it's very much still an open question really, whether the ground state is really a gapped or a gapless spin liquid. Clearly resonance is lowering the energy a lot, but is it a gapped or a gapless spin liquid? Is it a Z2 or a Dirac spin liquid? So there are a number of papers just within the last year, the last 6 months actually. First of all, there is this variational calculation by Iqbal, Becca and Paul Blanc, which argued that it is actually a gapless spin liquid. But these papers, first of all, DMRG, although people have argued for this gapped Z2 spin liquid, they have not seen certain topological degeneracies that are known to exist in such a Z2 spin liquid in the numerical studies. And this work by Xiaogang Wen and collaborators using tensor network methods argued for a Z2 spin liquid. This was more mixed about Z2 versus Dirac spin liquid, but these two papers very strongly favor a gapless Dirac spin liquid. So let me just very briefly mention this last one because it introduces some new ideas really. What these authors argue is that the reason why DMRG has been seeing a gapped spin liquid is because they are looking at this very special geometry of a cylinder. So if we remember from the study of carbon nanotubes, cylinders, if you have a Dirac spin liquid is supposed to be a system where you have Dirac cones. In other words, as in momentum space, there is a particular point where you have gapless excitations. Okay, so maybe 2 points in momentum space in the Brillouin zone where you have gapless excitations. But if you fold the system into a cylinder, then the allowed momenta are only along certain lines, and those can miss those special points, okay, depending on how you fold them. And then if you miss those Q points, then of course you are going to see a gap. So their idea was that what one wants to do is, rather than having the normal folding of the cylinder, we can try folding this A point, let us say, to over here or over here, we can put a twist there. First of all, that can change the lines that are allowed for this, for the system, or we can put a flux through this system, and the flux means that in the transverse direction you can add an additional phase factor, and these should actually cause, if it is a Dirac spin liquid, either of these things should end up closing the gap. Now, as you can see in their data, this is the data over here, applying these things, causing, you know, different kind of boundaries as well as applying this does reduce their gap, but it does not quite close it to 0, and in fact they, at the end they argue that the DMRG method should break down by the time you end up close to this gapless spin liquid. So again, just to address David's point over here, there is the more recently people have managed to go beyond the 36 site system to 42 and 48 site system, and some of the early arguments that DMRG people were making that 36 was very special and that is why it had huge number of singlets below the lowest triplet is simply not true. This feature of what is shown over here is not, it is not important. These are again the quantum numbers of the system as of, and this is the excitation energy, but what you see is the red are the triplet states and the open circles are the singlet states. Again you have huge number of singlets whether you go to 42 or 48, and this is not even a complete diagonalization. These are Landshaw's type methods that can pick up most of the low lying states but not all, and you can see that you have huge number of singlet states still below the lowest triplet state, and DMRG simply has not found this evidence for very small singlet gap and a much larger triplet gap and this huge singlet state degeneracy. So I think there is still something to be learned about these models. Okay, let me just very briefly then talk about the materials. So these Herbertsmithites are really they have zinc and copper transition metal ions. So they are basically they have this pyrochlore structure which is a layered structure, has this property. Ideally all the copper spins form these Kagome lattices and all the zinc spins they sit in the middle and they form what are called triangular planes in the middle. And if zinc is non-magnetic and copper is magnetic, you have really magnetically well isolated Kagome layers. Okay, that's this is the beautiful green color of copper here. That's people have been able to make very large single crystals which are needed for neutron scattering experiments. And this material one can easily show by just by comparing, for example, the susceptibility that it has. If you think in terms of the Heisenberg model, it has an exchange energy scale of order 200 Kelvin, but down to a few millikelvins that people have gone to, the system shows no sign of long range order. So that is the first sign that possibly it could be a spin liquid. But unfortunately the one thing that is present in these materials is disorder. I mean no materials are really free of disorder, but in this case there is a non-negligible amount of what I call anti-site disorder. That is, some of the zinc gets replaced by copper, and that means you have additional spins, and that means that it is hard to tell whether the system is gapless or not, because gapless excitations can come from these additional spins rather than from the Kagome system. Okay. So now if we think of this, does the high frequency dynamics remain affected, and are impurities first of all in the plane? If the impurities actually go in the planes, if some of these coppers get replaced by zinc, then clearly the Kagome system itself will get corrupted and will get highly diluted. So can we really tell whether this is still described well by a Heisenberg model, and does it still represent a quantum spin liquid? Okay, that is the question. So first, this is the experiment that got a lot of attention. This is also published in Nature by Han et al. And Young Lee is the main is the leader of that group, was at MIT at the time, now has moved to SLAC. So this is a neutron scattering experiment, and the theory this is that I am showing here is by Subir Sachdev and his group, who basically compare experiments with a particular type of Z2 spin liquid where we have spin-ons interacting with these the gauge excitations which are called Wisons, and this is the lower panel is the theory, the upper one is experiments, and what is shown is kx and ky, and the intensity of the scattering is at a given energy basically, or energy or frequency is shown by the color here. So of course the most prominent feature is the absence of scattering near the center of the Brillouin zone, and the scattering is mostly along the zone boundary, and furthermore as you go from high energy, this scattering is almost featureless basically, just as the same as the seen in experiments, but at lower energy it tends to concentrate a bit more on these so called M points. Okay, that is kind of what is seen in the experiments over here, and actually this theory is somewhat phenomenological, but even if you just do an exact diagonalization, you see kind of qualitatively these features already reflected in the properties of the system on a small cluster basically. So this is certainly some evidence that the system is forming a quantum spin liquid. One
sorry, Basil. This is very interesting. What if they start with, like, say, you want spin liquid? Can that be used to expand the data? Right.
So I was just going to show the next one. So that question is a very good question. Subir and they actually tried a few different cases, and the only thing that you will not be able to easily explain is this feature over here, that it starts to concentrate at these points in a certain way. But just getting this feature over here, that you have nothing, no scattering in these regions, and the scattering is mostly in this continuum, you will get that rather easily, as you can see in the next example here. So this is a very different system. There is a triangular lattice where the claim is that you have a gapless spin liquid with a Fermi surface and so on, just like what you were saying. This is the work done by this Chinese group over here, and as you can see, this is a triangular lattice, not even a Kagome lattice, but this of course their Brillouin zones are identical, because the underlying Brillouin zone of triangular and Kagome systems are, you see the feature that you have no scattering along these regions and only scattering in the middle over here near this is identical in these two systems. The only difference is really what is the structure within this, and these guys claim that this is well explained by having this kind of a gapless spin liquid, although they do not quantitatively get right, the features within, they do not try to get it right. Okay, so in that sense, exactly what kind of spin liquid you have is all about detailed structure within the continuum. If you just look for a continuum, that does not really let you distinguish between one type of spin liquid and another.
So the keys are the contribution from the gauge bosons, I guess.
They put that, so okay, that's put in phenomenologically. So they have in this, there is no completely kosher calculation of a spin on gauge degrees of freedom, everything included. So what these guys do is basically they start with what is called a Schwinger boson approximation of the mean field approximation of the spin degrees of freedom. From there they get the spin on spectrum, from there they get the spin on, and then they put by hand Wison, which are the gauge degrees of freedom, and they have a phenomenological model of spin ons and Wisons. Okay, and then they try different kinds of Wisons, so different kind of Z2, so this is only within Z2, different kinds of Z2 spin liquids, and they found they see that there is one type of Z2 spin liquid that can actually reproduce the way the structure develops in momentum space over here. So that is the argument, but it is phenomenological, it is not done completely starting with some microscopic model. Very difficult, yeah.
As you sharply point out, even you don't know how you couple your, the spin-ons to the experimental particles, right?
That's right.
You already mentioned that. So this has to be guessed.
Yeah. Okay. So finally, the NMR experiment was done by Takashi Imai in his group, and this is also published in Science. I mean, this is, so the good thing about NMR is that it's a very local probe. The nucleus can act as a probe of the electronic system, basically the electronic fluctuations, spin fluctuations very close to where the nucleus is. So even if we have impurities, if the impurities really are in this let us say, what I am showing over here, let us say these blue guys are actually the copper spins. This is where a zinc spin would have been, but let us say there is a copper defect over here, and these blue guys are again the copper spins. And suppose we do an oxygen NMR, then the oxygen spins which are right next to this defect will show a slightly different signature. The oxygens which are second neighbors or next nearest neighbor will show a slightly different signatures, and their argument basically of Imai and collaborators is that oxygens which are further away from nearest neighbor, they give a separate signature. So these they call the main guys, that is mostly looking at the pristine Kagome behavior, and the NMR spectra you can separate out these nearest neighbors and the next nearest neighbors. You know what their count should be and what their intensity should be from the main line. So one can just focus on the main line over here, and one can then look at the night shift associated with this main line. One finds that activated behavior as you expect for a gap, and that gap becomes smaller and smaller as you apply a bigger and bigger magnetic field. So this is the magnetic field and this is the gap, and you plot this, and then you can extrapolate down to 0 field from this and get an estimate for the gap, which is actually quite consistent with a value which is of order j over 20. So this is really experimental evidence that the system actually forms a gapped spin liquid. What we have done more recently working with Takashi Imai is basically calculate nuclear relaxation rate, but I guess in the interest of time I am just going to be very brief over here. So the nuclear relaxation rate can be, if we know the way the spins couple to the electronic spin degree of freedom, basically the nuclear relaxation rate can be related to the autocorrelation function of the spin variable, but calculating these autocorrelation function, but the frequency, the nuclear relaxation frequencies are very low. So essentially we are interested in the 0 frequency limit. That becomes a very challenging problem because of these delta functions over here, and the energy levels keep shifting from one cluster to another. So we use partly we use Moria's Gaussian approximation, which one can do in the thermodynamic limit, but we can also do more frequency moments, and we can calculate frequency moments, and basically by using computational methods such as the numerical linked cluster method, and then we have to assume some kind of an appropriate line shape, which we assume is a Lorentzian, but then we have to assume also a cutoff because all frequency moments are finite. So the system cannot simply have a Lorentzian line shape, and then by inverting this information we try to reconstruct the line shapes, and then basically our calculations break down at low temperature, but at high temperatures they represent the experimental data very well with no adjustable parameters really, because the hyperfine couplings are known, the exchange constants are also known from other experiments or from first principles calculation really. So that suggests that the Kagome system is still reasonably well described by just the Heisenberg model. At lower temperature clearly our calculation breaks down, which is the most interesting region, and we intend to in future try to use the DMRG to get finite temperature, low temperature properties really of this system. Okay. There is also a very recent neutron scattering experiment where people claim to confirm this NMR, saying that these, so we have these Kagome planes and then we have these zinc planes, triangular planes, some of which are zinc has been replaced by copper, that these have of course low energy spin correlations, but these low energy spin correlations have a z axis dispersion. So this is the plot of the intensity at low energies as a function of the z momentum, and you see that there is a change with z momentum, that is telling you that somehow it is coupling the spins between the planes. So there is no such z axis dispersion at higher energies, but there is at very low energy, and this is coming because these free spins are getting coupled with each other. Okay. I'm going to just quickly just stop over here. So the short answer is that they claim they can understand this thing very well, and in fact they can subtract this out, and when they do that, even neutron scattering gets a gap which is of order j over 20. So as a conclusion, the Kagome Lattice Heisenberg model is one of the simplest realistic model for realizing a quantum spin liquid. We certainly the Herbertsmithites, these materials are reasonably described by a nearest neighbor Kagome Lattice Heisenberg model, both at high temperatures and at short length scales as seen in the neutron scattering. Just a Heisenberg model seems to be sufficient for describing the properties, but the question remains, can a more definitive answer on the nature of the spin liquid phase be obtained in theory or experiments? We are close, but we do not quite have a definitive answer yet. And one could also ask this question, does the true ground state actually matter? Is the Kagome model, this is a different going in a different direction, is the Kagome model really too fine tuned or does it represent generic behavior? I mean, it seems that the pure Kagome Lattice Heisenberg model ground state, almost any kind of state one can think of has very, very low energy. So that seems rather unusual, and is that really a generic situation, or is the model really too fine tuned, and so should one even worry about the exact ground state of such a model? Okay, so on that note I will finish. Thank you.
You calculate using Heisenberg model for high temperature, it fits well with the experiment. What kind of method do you use to calculate?
Okay, so we used something called a numerical linked cluster method, which is like high temperature expansion. It's very similar to high temperature expansion, except instead of doing an expansion in a parameter like 1 over the temperature, we use the cluster sizes themselves as a expansion parameter.
Okay, so starting point is already like it's limited to high temperature region.
That's right. Yeah.
Confused about this continuum that you showed. If I think in terms of very naive quasi-particle picture, I would expect a broader Lorentzian and background typically.
Yes.
And that would be consistent with a Fermi
Yes.
calculation for 1 over T1 and 1 over T2.
Yes.
But what happens here? Is the continuum just a broad continuum, or these are quasi-particle?
So you have quasi-particles, but quasi-particles have fractional quantum numbers, and so the nucleus or the photon or the neutron, they cannot directly couple to that. They can only couple to pairs of these things, and so in that sense, they only couple to the continuum. So there is a quasi-particle, but that quasi-particle is a spin-on, which is is not allowed to couple to any external degree, and the nucleus itself is also an external degree of freedom. Nucleus can only couple to a normal quantum number object. Okay, so the coupling between the hyperfine coupling.
But that's still connected to the vacuum by the spin operator, right?
Yes. Yes, so the coupling between, say, the nuclear spin and the electronic spin, this must involve a spin operator. It cannot operate a spin-on, it cannot involve a spin-on operator. Okay, so that means that it can only either create two spin-ons, or it can create a spin-on and destroy a spin-on. Okay, so it can only couple to two particles at a time, and that changes the response that one gets. So again, that kind of a picture one can develop from very low temperatures, although that has not really been done in this case. So one has not. So Subir, Sachdev and collaborators, they try to fit the neutron data, but they don't even try to go to very low frequencies.
And in principle, those are the excitations that will determine the 1 over T1, right?
Yes, they are, yeah, but in combination, right.